Hello all, this is lecture 9 of Engineering Mathematics from the University of Notre Dame. So we will continue with our lectures on linear algebra, discussing today about independence of vectors, basis, and the dimension of subspaces. As always, we follow closely our textbook of Professor Strang, mainly lectures today 3.3, 3.4, and 3.5 for those interested to know more details on the subject area. So let's first try to review the lecture today. So we will identify first what independence means for vectors. And in many occasions, it helps to affiliate vectors with the columns of a matrix and effectively posing the problem of independence of vectors as identifying the null space of the corresponding matrix A. So if the null space has only the zero vector as a solution, then we know that the columns of the matrix A are independent. So in many ways, you can use this as a way to test the independence of vectors, and we have seen before various methods for identifying the details of the null space of a matrix A. So in general, if I have a number of vectors, and here are denoted as V1 to Vk, independence of these vectors means if I take any linear combination with any constants C1 to Ck, and this comes to be equal to 0, then the only way for this to take place is for all the C's to be equal to 0. Okay, so effectively you can look at these equations. If, let's say, C1 turns not to be 0, effectively this equation means that you'll be able to write V1 as a linear combination of V2 to Vk, and that's sort of an equivalent definition of independence of vectors. If we have a matrix, and the matrix has m rows and n columns, we know that this matrix has a non-zero null space, so the columns are, we have too many columns that they are dependent, and you can see this because this matrix has a rank that at very best is equal to m, so there is n minus m free variables that define a non-zero null space. Right, so in that case, you will know that this problem leads to dependent columns. So we will see today, and I have discussed this in, I think, in earlier lectures, the concept of a span of a set of vectors. So if I give you a bunch of vectors, V1 to Vk, and you take linear combinations, then I call the space that is derived that way the span of V1 to Vk. And equivalently, if you have a space S, you will say that V1 to Vk is a span for this space S if every vector in S can be written as a linear combinations of the vectors V1 to Vk. Now, if I give you a space S, right, so you can have various sets of vectors that span that space S. If you are looking for the minimum set of vectors that span the space S, then these vectors form a basis for that space, and they are independent vectors. Okay, so in essence, they identify what we call the basis for S, and so it's a minimum set of linear independent vectors that can generate by linear combinations any vectors in S, and we define that to be the basis of the space S. Now, if you have a basis for the space S, and a number of vectors in that basis, then the number of that vectors is called the dimension of the space S. So if you can think of this as the dimension being the minimum set of vectors that obviously need to be linear independent that generate every other vector in the space S. So the vectors basically need to span the space, and they need to be independent to form a basis for that space. And we will see lots of examples where the number of the elements in the basis will always be the same, but the actual vectors in the basis don't have to be the same. So the definition of a basis is leads to the dimensionality that is always the same, but the actual members of the basis, they don't have to be the same vectors. Okay, so we will see many examples of that. So if, since we're going to play with lots of vectors in the Rn dimension, so if you have the space, let's say R4, and you have a matrix A that is 4 by 4 that is invertible, then the columns of that matrix basically is a basis for R4. And you may want to ask yourselves how many invertible 4 by 4 matrices I have. Well, you have infinite of those. And in many ways, the columns of all of these matrices are basis for R4. Okay, so you can see again that the basis consists of vectors that they are not unique, but they're all independent, and they all, when we put together, they span the space R4. So that's sort of a very brief summary of the lecture, and in some sense, this slide, following again the Professor Strang's book, identifies all the essential topics for the lecture today. Okay, so let's talk a little bit about this independence of vectors and concentrate with the columns now of a matrix. So if somebody gives you a matrix M by N, you may have already been able to extract the idea here that the numbers M and N, they are not really the true dimension of the matrix A, because it's very possible, as we have seen, that many of the rows of the matrix are linear combinations of the earlier rows. So when you do elimination, a lot of these rows become zero. The true dimension of the column space is really the rank R of the matrix, and that's from where the idea of independence of the vectors comes. Of course, you don't need to refer to a matrix to talk about independence, and you can think of any vectors in any vector space and talk about the independence of these vectors. So independent vectors span the space, and it is the minimum set of vectors that can generate a given space. They're not too many, they're not too few, they're just right to generate a space. So, so independent vectors, I just said it, if you have a space, they're just the right number, the minimum number of vectors that you need to span that space. Now, spanning a space, you can do it, let's say if you have the space of R4, you can do this with 50 vectors in R4, or you can just do it with 4 independent vectors in R4. And in both cases, the 50 vectors or the 4 vectors span the space, but we're really interested in the minimum set of vectors that are necessary to span a space, and those vectors are independent vectors, and they form, as we have seen, a basis. So a basis for a space, there are this number of independent vectors that there are not too many of those. There are not 50 for, let's say, the space R4. There are not 3 for R4. There's just 4, which is just the right number to be able to generate any other vector in R4. And the number of the vectors in a basis is what we call the dimension of a space. So the dimension of R4 is 4 because you need 4 vectors to generate any other vector in R4. So you can think of those vectors being, for example, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Okay, this actually is what we will call later on the standard basis for the R4 and in general the Rn space. Okay, so we have affiliated already the independent columns with matrices A that have as the only solution to the null space problem the solution x equal to 0. So this is in many ways a nice test to investigate the independence of vectors. So you make them columns of a matrix A, and if you know how to compute the solution to the null space problem in an efficient manner, for example, through elimination, then you can immediately see if a number of vectors are independent. Actually, for me, this is the preferable way that I would like everybody to check independence. So when I ask you to check if vectors are independent, put them as columns of a matrix, evaluate the null space, and make your decisions by looking if the null space has or not non-zero solutions. Okay, so let's look at a very particular example so we can affiliate this with geometry. So you can take 3 vectors in R cube, and we will try to identify 3 vectors that they are independent and 3 vectors W1 to W3 that they are dependent, and see what is the familiar view that we get from geometry. So if the 3 vectors are independent, you all know, let me go back. So we all know the independence of the 3 vectors basically implies that they are not on the same plane. So in this case, you have 2 vectors, v2, v3 on a plane, and then you have v1 normal to that plane. Obviously, these vectors from your experience are what we already have called independent vectors. And then here is another case of 3 vectors that they're all in the plane, and you can see the dependence of these vectors because in this particular case W2 is W1 plus W3. So actually you can write a combination of the 3 vectors, in this case W1 minus W2 plus W3 equal to 0, where the coefficients, as you see, are not 0. It's 1, minus 1, and 1. So in this case the 3 vectors are dependent. In practice, that implying that you can write one as a linear combination of the other 2 vectors. In this case, you can try to take combinations of the vectors v1, v2, v3. You will see that the only combination that gives you a vector that is equal to 0 vector is when the coefficients are all equal to 0. If again you try to do this with linear algebra, you will take these 3 vectors in R cube in this case, put them as columns of a 3 by 3 matrix, and then you can compute the null space, and you will find out that in this case, after elimination, the null space has only the 0 solution. In this case, the null space will have a solution that includes vectors such as 1, minus 1, and 1. So, okay. This definition sort of is very natural. You have, so you can test for any sets of vectors. So let me just summarize that if you're given a bunch of vectors, v1 to vn, from some vector space, the linear independence implies that the only combination of these vectors that gives you the 0 vector is basically a combination with all the coefficients equal to 0. Okay. If it happens, again, that you can find some combination with some of the coefficients not zero, effectively means that one vector can be written as a combination of the other vectors, and this is what we call when we say that the vectors are dependent. So a few examples, more examples in this case in R2. If you take the vectors 1, 0, and 0, 1, they are independent. All right. As a matter of fact, we will see they form the standard basis for the R2 space. But also, if you look at these two vectors, even though this number here is very close to 0, they're still independent. Okay. So these two vectors are independent, and as a matter of fact, they form a basis of R2, which reminds you that the basis is not unique. Of course, 1, 0, and 0, 1 is the standard basis, but somebody can take this weird basis 1, 0, and 1, 0, 0, 0, 1. Now, if we take these two vectors, you can see immediately they are dependent because you can take a linear combination of them. So 1 times this vector and 1 times this vector, you will get the 0 vector, and the coefficients in the combination will be non-zero, so these vectors are dependent. Obviously, in other words, you can see that this second vector is minus 1 time the first vector. If you take now the vector 1, 1 and the vector 0, 0, these vectors are dependent because you can look at it, right? You can take the vector 0, 0 and write it, the vector 0, 0, you can write it as 0 times the vector 1, 1. So the 0, 0 vector can be written as a combination of any other vectors, which means something extremely important. You should never have the 0 vector in a set of independent vectors. The 0 vector should not ever be in a basis because basically it destroys independence of vectors. Okay, so in this case, you can see the 1, 1 and 0, 0 are dependent. Never allow or claim that the set of vectors that includes the 0 vector are independent. That is not the case. And let me finish in R2. If you have 3 vectors, A, B, C, D, E, F, you know that these 3 vectors cannot be independent because you only need 2 vectors in R2 to generate any other vector. So if somebody gives you 3 vectors, you know that one of those vectors have to be dependent on the other 2. Now, of course, I don't imply without any specific numbers here that these 3 vectors span the space R2, because it's very possible that all 3 vectors are parallel to each other, so the dimensionality of the subspace is 1 and it's not 2. But if 2 of these vectors are independent, then they span the whole of R2. Okay, so before I mention that the obvious way to look that these 2 vectors are dependent, but if I give you a homework problem, or you have to demonstrate that you are learning useful things from this class, if somebody asks you to show that the vector 1, 1 and minus 1, minus 1 are dependent, what you really need to do is just make them the columns of a matrix, as I indicate here, and compute the null space of this matrix A. So obviously the null space, if you put x equal to 1, x1 equal to 1, x2 equal to 1, you see that that's a solution. So immediately you know that these 2 column vectors cannot be independent. Okay, this is a very good way to test this, not just in 2 dimensions, but you can test this in any dimensions. All right, so we have seen that 3 vectors in R2 cannot be independent, and if you try to be serious in proving this, rather than using sort of common sense argument and say this is trivial, it's obvious. What you can do, make those three vectors the columns of a 2 by 3 matrix, and then try to compute the rank and the null space solutions, and immediately you will see that three vectors cannot be independent, because you will identify that the null space has a non-zero solution. Okay, again, this is a good way to demonstrate the role of linear algebra in testing linear independence of vectors. Now, in elementary courses in linear algebra, maybe you are not going to compute the rank and the null space of a matrix. What you will do is you will try to put maybe one vector as a combination of the other two by playing around and trying to guess, or just doing some linear algebra calculations. But we do have a good way through the null space evaluation through the free vectors to actually address this type of a problem. All right. So let me take one more example. Infinite examples on this lecture. So if you want to check the independence of these three vectors, we put them as columns of a 3 by 3 matrix, and you can immediately see that there is a non-zero solution to the null space problem, because if you test the numbers here, minus 3, 1, 1, what actually you will get is you will get the zero vector. And remember, when you multiply A times X, you get linear combination of the columns. So effectively, you can actually see that the primitive definition of linear independence comes explicitly from the fact that there is a non-zero solution to the null space problem, because minus 3 times the column 1 plus column 2 plus column 3 gives you the zero vector. Now, again, in this case, 3 by 3, it's an easy way, it's a square matrix, easy way to actually see to discuss about linear independence. And actually, I immediately see a typo here, though. So this linear independence, these vectors are in R cube, so we need to correct this. So we'll correct in the posted slides. So the right way to do this using what you are learning in linear algebra is to actually do elimination, take this matrix, reduce it to the row echelon reduced matrix, and here is R. You can see you have two pivots, so you have two independent rows, two independent columns, and immediately you can see that you have one free vector, and actually that free vector immediately, based on what we have learned, is minus 3, 1, and 1. You remember, you need to reverse the signs of this F matrix here, so it becomes here minus 3, 1, and we only have one free vector, so we set it equal to 1, and that's the solution to the null space that we identify here by just looking carefully at the columns of this matrix A. Okay, so elimination, again, is the best way to test for any sizes of matrices, square or not, the independence of vectors. Now, let me just mention something that you will often come across. So we always play with matrices m by n. So if I give you a matrix that has m equal to 5 and n equal to 7, you know by things we have done with evaluation of the null space that the rank of that matrix is at least equal to m, in this case equal to 5, and we have at least 7 minus 5 free vectors. So the solution to the null space problem includes vectors that join the zero vector. So in that case, we know that these 7 columns of vectors in the R5 space, because they have 5 components, they need to be dependent. Okay, so this is a very general result for matrices that have n greater to m. So if you look at the columns that are in Rm, these n columns have to be dependent. So you can use this argument right away in any application where you have this type of matrices. Now, if it is very possible if you have the opposite, if m is greater or equal to n, basically in this case, what you need to do is, again, you need to do elimination. You need to find the pivot columns, okay, and so you have to identify the independent rows and columns, find the dimensionality of the null space, and somehow if n is less or equal to m, it is possible that the null space has only the zero solution, but depending on what you have there, you can also have columns that they are independent. Okay, so for example, if the matrix is M, let's say you have a matrix that the columns are in R7, and you have n equal to 3. Those 3 columns can be independent, right? But there is no reason it can also be dependent. Okay, we don't have the previous case where for sure if we have more columns than rows, we can say that there is an for sure non-zero solution to the null space problem. Here we may have one or we may not have one. Okay, so so a matrix that has 7 components in the column vectors, and we only have 5 of those vectors. Those 5 vectors can be independent, but also can be dependent. Now, all right, so we have introduced earlier the column space, Cfa, which is basically the space that the columns span. So if we have a matrix m by n, if the columns are independent, then they span the whole of Rm. If not, we will see exactly what is missing, but certainly the space that is being generated by linear combinations of columns, this is what we call the column space. So if you take this standard vectors v1 and v2 that you see in R2, certainly they span R2. But look at that. If you take 3 vectors in R2, the ones that you see here, v1 to v3, they also span R2. Remember, the definition of the span is not that these vectors are linear independent. The whole idea is if I take linear combinations of these vectors, I can generate everything in R2, and certainly because these 2 vectors are independent, that's sufficient to allow me by linear combination of v1, v2, v3 to generate anything else. Now, if you take these 2 vectors, obviously these 2 vectors span a line, these 2 vectors are dependent, and they can only generate vectors that they are on this line 1, 1. Okay, so they cannot span the whole of R2. Now, you may ask, why do we always say take these vectors and make them columns and discuss about the independence of columns? You can actually do the same thing with rows, and I'm not going to discuss this too much because it follows exactly the same idea. So if you look at the rows of a matrix, so for a matrix m by n, the rows are in Rn. You can define about the space that you get by taking combination of the rows, and that space is called the row space of the matrix. So we say that the rows span the row space, and again, these rows can be dependent, can be independent, so they can span the whole of Rn or maybe some subspace of Rn, and exactly as similar to the examples we have seen regarding the column space. All right, so the row space, we denote it as C of A transpose because effectively the row space is the column space of A transpose. If you take A transpose, you make the rows of A the columns of A transpose, and so you can talk about the row space, the linear combinations of the rows to be the same as the linear combination of the columns of A transpose. Okay, so this is the notation that we use for this subspace of Rn that we call the row space. So let me give another example. Here is A transpose, so M equal to 3, N is equal to 2. So the column space, you can see, just without doing anything here, these two columns, they look to be independent. So R is equal to 2 in this particular case. And obviously, you can, so we can, the column space basically is not sufficient to generate all vectors in R cube, but the two vectors that we have are independent. So if you want to ask, what type of, if you take the span of the two columns, what subspace of R cube they generate, because there are only two vectors, the subspace they generate is basically a plane in 3 dimensions. Now, if you take the row space, okay, so the row space, just looking at the matrix A, there are vectors in R2, okay, and I have 3 of those, so obviously they need to be dependent, but you notice that at least 2 of these vectors of the rows of A, they look to be independent, so the row space of A generates the whole of R2, okay, so I have enough independent vectors in the rows to generate by linear combination the whole of R2, okay. So again, the column space of A generates only a plane with linear combinations, is just a plane itself, and the row space of A, or the column space of A transpose, generates the whole of R2 in this particular case. So let's move along. I bring back the concept of a basis. Is basically a basis for a vector space needs to satisfy 2 fundamental properties. These vectors need to be able by linear combinations to generate that space, and they need to be the minimum set of vectors that can do that, and as such, they need to be linearly independent. So basis vectors need to be linearly independent, and they need to span the space. We already have referred to this, but the number of the vectors in a basis of a space is called the dimension of that space, and it's actually a unique number. And I'm going to try to prove it before we end the lecture today on a follow-up slide. So for now, let me say the following. If you have a basis V1, Vn to Vn for a vector space, any vector in that vector space can be written as a linear combination of V1 to Vn, okay? And what this particular theorem that you see on this slide says is that this combination, the coefficients that you have A1 to An is unique. So if I give you a basis and I give you a vector V, you can write it as a linear combination of the basis vectors in a unique manner. This is extremely important. The proof is trivial because you can go by contradiction and say, well, let's suppose I can write it in another form using these coefficients B1 to Bn. If that's the case, you can subtract the 2 equations, and then you get this nice equation where the 0 vector is this linear combination of the vectors with the coefficients being alpha 1 minus B1, alpha n minus Bn. And because these vectors V1 to Vn are independent, then all the coefficients have to be equal to 0, and then you get what you expect, that alpha I is equal to Bi. Later, in another lecture, we will see how to actually compute this vectors alpha 1 to alpha n for a very general basis. But right now, what you need to remember is if you have a vector V, there is a unique representation in terms of the basis vector. This is an extremely fundamental theorem in linear algebra. So let me give you once more for R2 the two standard basis vectors. Everybody knows, right, when you draw two unit vectors in on the plane, the standard basis vectors are the vectors 1, 0, and 0, 1, and this is what you see here. In general, these basis vectors are not unique, right? So you can take any matrix that is invertible in 2 by 2 and take the columns of that matrix. They form a basis for R2. And so what I have here is I have an invertible matrix 3 by 3, and you can do whatever test you want to verify that this is invertible. The columns of this matrix basically is a basis for RQ. And here is a matrix that is not invertible. And if you can verify that it's not invertible, if you take the 3 columns of that matrix, then they don't form a basis for RQ. Actually, you can see that this is not invertible because the third column is the sum of the first two columns. And again, if you really to formally want to actually do this type of calculations, what you will need to do to investigate invertibility and the existence of non-zero solutions to the null space problem is to basically do the elimination all the way to the R matrix, and at the end you decide if the matrix is invertible or not. So I remind you that when you form this R matrix, effectively is the pivot columns of A that form the basis for the column space. Because remember that the column vectors of the R matrix, they're not the same. The space they generate is not the same as the column space of the A matrix, because we did a lot of row operations. These row operations leave the row spaces of A and R unchanged, but they do affect the columns. So when you do elimination, what doesn't change are the pivot columns for both A and R. So you look at R, you decide what are your pivot columns, and then you select the corresponding pivot columns of A. That's the basis for the column space of A. So do not take the independent columns of R and take those as a basis for the matrix A. Those are a basis for R. For the column space of R, you need the corresponding basis for the column space of A. So take the same pivot columns, but select the columns of A to form the column space of A. Okay, we will see this and iterate this in several lectures, and also we will try to reinforce this idea through various homework problems. So if you look at this matrix here, 2, 4, 3, and 6, if you do elimination, you basically get that the rank is equal to 1. You can see you get your 0, zeros because effectively the second row is in the same direction as the first row, so the second row was eliminated. You have one pivot column, and obviously you have a non-zero element in the null space, and effectively you look at the one pivot column, so 1, 0 is the basis vector for the column space of R, but if you want the column space of A, that is the vector 2, 3 that corresponds to the first, to the pivot column that you identify through the R matrix. So I believe on the second slide I give you a summary of this. So the basis for the column space here is the vector 2, 3, and the basis for the row space is the vector 1, 2, which is the same for R and A, okay, because we manipulated A with linear combinations of rows, and you can see the vector 1, 2 is the vector 1, 2 is half basically of the vector 2, 4, okay, so they are in the same direction. So the basis for the row space is 1, 2, but the basis for the column space in this case is 2, 3. Now, when you do lots of examples with this, you realize that there are multiple ways to identify independent columns on a big matrix, right? But the natural way for us to do this type of calculations is to select the pivot columns of A as the basis for the column space of A. Okay, there may be other bases, but the one that we use is the one that corresponds to the pivot columns of A. Okay, all right, so we discuss this to be careful with the selection of a basis for the column space. So here is the elimination process for some matrix A that effectively it gives you pivot columns 1 and 3. So you have to be careful here. If somebody asks you to calculate the column space of A, you are going to have to take columns 1 and 3 of A. Okay, this is very essential. Okay, now if you want to have a basis for the row space of A and R, you can take as a basis the vectors 1, 2, 0, 3 and 0, 0, 1, 4. That will be the same for both the row space of A and the row space of R. All right, so that's good enough. So let me discuss something that I think I referred to before. And, you know, I'm going to bypass all of these things here. And so the question that I brought up before is that we have many basis vectors for a vector space, but somehow the dimensionality, the number of the vectors in each base is always the same. And we never really prove this. We assume that's the case. So this is a good time to actually show a proof. And I'm going to try to highlight it very fast. And the slides are self-explanatory, so you can actually read them and convince yourselves that that's the case. So let's do the following thing. Let's take a vector space, and let's say we have vectors v1 to vm that forms a basis. So that's a basis of the space, and w1 to wn that form a basis. And the idea here is to prove that m is equal to n. So both the v vectors and the w vectors, we take them to be bases of the vector space, of the same vector space, and we need to prove that m is equal to n. So what we're going to do is we're going to try to assume that n is greater than m. And actually, you'll be able to repeat the same calculations if m is greater than n, but let's do n greater than m and try to see why this leads to a contradiction. So if n is greater than m, what I'm going to do is, and you see this in the equation on the bottom, I take each of the w vectors and I'm writing them as a linear combination of the vectors v. Remember, a basis can generate any vector, so the v's should be able to generate every w. And you can see w1 is v1, v2 to vm times the first column, w2 is this v's times the second column, etc. So I call this the v matrix. I call this the A matrix, and the vectors with the w's as columns is my W matrix. Notice that the A matrix has more columns than rows because I assume that n is greater than m. Now, what do we know if we have a matrix that has more columns than rows? We know that has a non-zero solution to the null space problem. So effectively, we know that there is an x that is everything zero, such that ax equal to 0. If that is the case, and there is such an x that has a non-zero solution, we can multiply this equation ax equal to 0 with v. And so let me do that. From ax equal to 0, I can write vax equal to 0. But v times a is w, is the w matrix. So I get wx equal to 0. And what is wx? It's basically a linear combination without having zero coefficients, because we said not all x's are 0. So it's a linear combination of the w vectors, of the vectors on my w basis. But that's not possible because if the little w's form a basis for the vector space, then any linear combination that gives you the 0 vector needs to have all the coefficients equal to 0. So effectively what we got is a contradiction. And why we get a contradiction? Because we assume that n is greater than m. Similarly, you can try with m greater than n, and you will get a similar contradiction. So the only solution you have is for m is equal to n, and that's why the concept of dimension of a vector space comes to be fundamental. Every basis of that space has the same number of independent vectors, but the basis is not unique. But the dimension, it's a unique number that identifies that space. All right, so this is extremely important concept for our linear algebra part of the course. Okay, so the dimension of the space is the number of vectors in every basis. So if you take a line through this in R cube, through in this direction, 1, 5, and 2, then looking at that line as a subspace of R cube has dimensionality 1, because the vector v generates any other vector by multiplying it with a constant. If you take a plane, x plus 5, y plus 2 is equal to 0, this plane is a subspace in R cube, and it's a two-dimensional subspace. And you can show that actually has, it consists basically by linear combination of these vectors from the null space, that they are the vectors minus 5, 1, 0, and the vector minus 2, 0, 1. So you have two free vectors, and the dimension is 2. And if you think I got these numbers out of nowhere, to start with, somebody can say, how do I generate these numbers? I took y equal to 0, y equal to 1 and z equal to 0 to get this. And then I took z equal to 1 and y equal to 0 to get that. But the actual best way to do this is, I'm not quite sure. Let me see if I have it yet here. So you can actually look at this plane as the null space of a matrix that is 1, 5, 2. This matrix has only one pivot column, has two free variables, and immediately you can read the basis for the null space as being minus 5, 1, 0, and minus 2, 0, 1. Remember, we changed the signs on 5 and 2, and we put the free variables to 1, 0, and 0, 1 values to get the non-zero solutions to the null space problem. So a plane in 3 dimensions is a 2-dimensional subspace. A line is a 1-dimensional subspace. I think you have to do a homework problem that involves this type of calculations, but practically it is similar, if not the same, as what you see on this slide. So for the n by n matrix, we have n minus r special solutions that form a basis for the null space. The column space has dimensionality r, so the basis vectors, there are of those, okay? And the dimensionality of the null space, again, is n minus r. Now, let me try to generalize things so we can finish this lecture. We talked about vectors, but vectors, you can use it in a liberal sense. They don't have to be vectors in Rn. So you can think of a vector space that consists of matrices of the same size. And so, for example, you can look in a vector space of matrices, a vector space that has elements that their matrices 3 by 4, and you can ask yourself, what is the basis for that space of matrices 3 by 4? How many independent matrices do I need to generate any other matrices in 3 by 4? And I'm going to demonstrate. The answer is actually you're going to need 12, right? 3 times 4. And you're going to need 12 basis matrices or elements in the basis to be able to generate any arbitrary matrix of 3 by 4. But I'm going to show you this in 2 by 2. So what you see there is a basis for 2 by 2 matrices. Obviously, you can convince yourself that any matrix that is 2 by 2, it's a linear combination of this. You can also convince yourselves that if you take a linear combination and you set it equal to 0, then all the coefficients have to be equal to 0. And this has to do with the nice structure that we have here, only one element being equal to 1 and the rest equal to 0. That is what, at the end of the day, enforces independency of these matrices A1, A2, A3, and A4. Now, if you have an n by n matrix and you're asking what's the dimensionality of a general n by n matrix, is if you think trying to do this generation of a basis for an n by n matrix, then you're going to need n squared type of elements in the basis of that space of matrices, all right? So n squared is the dimensionality of the spaces of the space of matrices of size n by n. Now, you know, there is a lot of matrices in that you will see in engineering and in your applications that have some structure. So some matrices, we already have seen them. They are diagonal. Some matrices, they are upper triangular. Some matrices are symmetric. So you may ask, what is the basis for diagonal matrices? And you can immediately see the basis. You can generate a basis for a diagonal matrix by only keeping A1 and A4. You can generate a basis for upper triangular matrices by keeping A1, A4, and A2. You can generate a basis for lower triangular matrices by keeping A1, A3, and A4. Remember, lower and upper triangular still have non-zero diagonal elements. And if it happens that you want the basis for a symmetric matrix 2 by 2, you need to keep A1, A4, and then you need to combine this together to a new basis matrix that is A2 plus A3. So you will need to have 1 in and 1 in the off diagonal to be able to generate symmetric matrices. And matrices that have a structure are extremely important because they simplify quite often the calculations because we will try to take advantage of the particular structure. Now, without any proof, and actually you can do the algebra on your own. If you have a general n by n matrix, the dimensionality is n squared. If the matrix is upper triangular, the dimensionality is n squared by 2 plus n by 2. Effectively, how you get this number, count how many elements you have for an upper triangular matrix, counting also the diagonal elements. And that number comes to be what you see here. If you have a diagonal matrix, then you have n elements. And if you have a symmetric matrix, you have basically the same number as before, n squared over 2 plus n over 2 being the dimensionality for a symmetric matrix. You can push this concept of basis of a vector space and actually start talking about functions. Somebody can talk about the differential equation and the space that consists of the solutions of this differential equation. And this differential equation, you should remember that has two solutions, e to the x and e to the minus x. So you know these two functions constitute the basis in the space of solutions of these differential equations, and the basis is two-dimensional. There are two basis elements that they are independent, and the number 2 has very much to do with the order of the differential equation that in this case comes to be equal to 2. Here is another differential equation, right? So we have y second derivative equal to minus y, so the solutions are sines and cosines. So the space of solutions here, which is a function space, has a basis sine x and cosine x. So still two-dimensional because the order of the differential equation is 2. And here is back the same thing we had in the previous slide where the basis consists of e to the x and e to the minus x. And again, like with vector spaces that we have seen, the identification of the basis is not unique, but the number of independent vectors, or in this case functions in the space on the basis, is that number is unique, and that is the basis to the solutions of the differential equation. The idea here is, in linear algebra, we solve equations, linear system of equations like AX equal B, and we use the machinery of linear algebra. We can sort of envision the same sort of operations and the same sort of algebra. The only difference is, rather than manipulating linearly rows and columns, we're going to be using the machinery of calculus to do similar calculations as the ones that we have seen up to now in this course. In talking about differential equations and the basis, let me say something about the null space of the differential equations to see if there is any analogy in what you learned in what we learned in in this linear algebra lecture. So I am taking a differential equation which is homogeneous, and so y double prime equal to 0. So this has a linear solution which is a constant times x plus some constant. So basically, the solution to the null space problem that corresponds to this homogeneous equation are the functions 1, right, from this term, and the function x. So the null space has dimensionality 2 in this particular problem. And if you look now at the non-homogeneous equation, so you have y double prime equal to 2, this has a particular solution the same way we have seen particular solutions to linear algebra. So for example, if you try x squared and you take second derivatives, you get y double prime equal to 2. So the general solution is what? Is the particular solution x squared plus the solution to the null space problem. Exactly what you have learned in linear algebra. The difference is the calculations are calculations based in calculus and differential equations rather than based on linear algebra. All right, we're almost done, so let me just refer to the space Z that includes only the 0 vector. The empty set is a basis for Z, and Z contains only the 0 element, so the 0 element is the basis for Z. And I remind you never to put in any independent set of vectors the 0 vector, because it destroys independence. But this space Z of 0 elements comes to be essential in algebra and in various derivations that we will see later on. So remember, the space Z is the space that contains only the 0 vector. Okay, it contains only the 0 vector. So the dimensionality of this space is 0. So it has only the 0 element, dimensionality is 0, and so it will be essential. Okay, we will see actually later on that some spaces, they only meet at the 0 vector. Okay, and so if you try to identify a common subspace of two spaces, you will see that that common subspace will come to be the Z space, only the 0 point. So we are finishing up, and we talked about independence. We affiliated that with the null space problem. We discussed about a set of vectors spanning a space, and also a set of vectors forming a basis for a space. So they have to be linear, independent. They need to be able to generate by linear combinations any arbitrary vector in that space. We define the dimension of a space as the number of elements in a basis of that space. And we talked about identifying a basis for the column space and the row space, and the essential elements there were things that we learned in elimination processes, such as the rank. So in many ways, you can think of an alternative definition of the rank as being the dimension of the column space and the dimension of the row space, because we have seen that all of these previous definitions are equivalent with what we learned in this course. So that's all for today, and I will see you next time in a follow-up lecture. Thank you.